Hello, everybody out there. Welcome to my channel. This channel is focused on educational development for people who are curious about some of the latest and greatest theories of everything and magnum opuses from obscure sources and um, esoteric writings that are a little bit hard to access, and any other type of, cosmologies or all-encompassing theories that might really benefit your life, but they're being suppressed and haven't really gotten to see the light of day. And today is our 397th video that we've done on the reciprocal system of theory of one Dewey B. Larson. Mr. Larson grew up in the United States and lived from 1898 until 1990. Around 1959, he put out his two fundamental postulates. After a few decades of working out the kinks, he put out just two short sentences about how the universe operates. And then over the next 30 years, he developed those fundamental postulates into a theoretical universe about, through a process of deduction, if this, then that. And if my two postulates are correct, then my universe would look like this. And so he took that theoretical universe and basically compared it to the actual empirical, I won't say actual, but the empirical universe of the modern scientists who had, these expensive laboratories and telescopes and atom smashers, and, they had compiled all kinds of data about the periodic table and all the different stars and galaxies that are out there, and so on. And Larson's universe, Larson's for free universe, or for minimal cost universe, compares quite strikingly with that of legacy science. And when there is a conflict, usually it seems like Mr. Larson's alternative works out better. So Mr. Larson, in my opinion, basically beat an army of well-funded scientists over the course of actually millennia. Just one dude with the powerful theory that he had and his ability to deduce. Today, so basically, the first fundamental postulate lays out most of the territory, and then the second postulate is just kind of almost a throw-in. The first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Now, one thing that Larson doesn't say in those 2 postulates is that when he says motion, he's referring to what he calls a scalar motion. A scalar motion is a motion that has a magnitude, but it has no specific direction. And it's something that you would envision using a balloon with dots on it. If you blow up the balloon, all of the dots will be moving away from each other. Every dot is moving away from every other dot. And even the locations between the dots are moving away from each other. but in no specific direction. That's a scalar motion. And that motion has been obviously observed by scientists, but never investigated for its significance until Larson came around. And he uses it as the foundation for what he's talking about. Now, yesterday we talked about how he talked about the concept of a distributed scalar motion. And that's basically if you take that motion and then you rotate it. And so the effect is basically spread out over the course of a rotation. And he uses that to explain many other things as well. So today is the second day that we've gone over his paper here that is called The Physics of Motion. And so if you want to listen to the first part of that paper, go back and listen to yesterday's video. He will go over in detail scalar motion and how he sees the importance of scalar motion and where it plugs into his theory. And we're going to go through the second part of that paper today. Hopefully finish it, but maybe not. And then, the other important part of the theory is just that motion is the relationship between space and time, which sets up a generalized reciprocal relationship between space and time that hasn't really been recognized. Even though if you look at the most basic kind of motion, speed, the car is moving 10 miles an hour, there is a reciprocal relationship between space and time. If you multiply the speed by 2, you can see that you can say, now the car is moving 20 miles per hour, 20 miles of space in 1 hour of time. Or, equivalently, you could also say that this car is now moving 10 miles per half hour. You can either multiply the space by 2, or you can divide the time by 2. A reciprocal relationship. So that is at least a prima facie demonstration that there is a reciprocal relationship between space and time. But he says that it is more all-encompassing than that, and he bases everything on that concept. So we are about to start a section in this paper, The Physics of Motion. It's called The Mystery of Electric Charge. Now, also keep in mind that in Larson's theory of electric charge has been very much maligned by some of Larson's followers. They feel that, especially Dr. Bruce Perret, feel that Larson got several things wrong about the electric charge, the electrical, magnetic and electrical systems in general. Okay. In conventional scientific thought, the electric charge is accepted as a given feature of the universe. Its properties are likewise accepted without explanation, either as to their origin or as to their nature. The charge manifests itself by exerting a force on objects of certain kinds within a certain region of space. A charge at point A, for instance, exerts a force on a test charge at point B, somewhere within its range. This effect appears to indicate the existence of action at a distance, a concept that is philosophically unacceptable to most present-day theorists. To avoid conceding reality to this objectionable process, they assume that the charge at location A is surrounded by a field. The force is thought to be transmitted through this field, and it is the field then that exerts a force on the test charge at location B. There is no clear understanding or general agreement as to what as to just what this hypothetical field actually is. Einstein contends that the charge, quote, calls into being something physically real in the space around it, and that this something is the field. Other physicists disagree. P.W. Bridgman dismisses the whole idea. Quote, it is only by an uncritical analogy, he says, that we form the concept of a field independently existing in its own right. He adds that instrumentally, the distinction between field and action at a distance appears to be meaningless. As the only feature of this situation of which we have actual knowledge is that the charge exerts a force, the first step toward a better understanding is to take a closer look at the concept of force, with particular reference to its relation to motion. Motion is measured on an individual mass unit basis as speed or velocity. That is, each mass unit moves at this rate. On a collective basis, motion is the product of mass and velocity, which is momentum, formerly called quantity of motion. Momentum equals mass times velocity. The time rate of change of the motion is acceleration on an individual mass unit basis, and it is force, the product of mass and acceleration, on a collective basis. Force equals mass times acceleration. Thus, force could legitimately be called quantity of acceleration, a term that would reflect its true nature. By definition, force is a property of an accelerated motion, not something that can exist in its own right. Wherever there is a force, there must be a motion of which the force is a property. Once this point is recognized, the role of force in physical action becomes clear. The basic physical process is the transfer of motion. Such a transfer consists of a simultaneous decrease in the magnitude of one motion, a negative acceleration, and an increase of equal magnitude, a positive acceleration, in another motion. The force or quantity of acceleration is a measure of the magnitude involved in the transfer. In firing a rocket, for example, the force exerted by the combustion products on the rocket is the quantity of acceleration transferred from these products. The product of the mass of the rocket and the acceleration imparted to it is the quantity of acceleration received by the rocket. Except for losses in the process, these two quantities are equal. The status of force in general as a quantity of acceleration, a property of a motion, obviously applies to the force exerted by an electric charge. But present-day physical science cannot find the motion of which the force must be a property. So far as the physicists are able to determine, the electric force originates directly from the charge, although they have been unable to discover how it originates. Furthermore, to the physicists, force is a vector quantity. That is, it has a specific direction as well as a magnitude. But the force exerted by the electric charge is not a vector. It is a distributed force, a field. These discrepancies have thrown the whole situation into confusion. In the wonderland of present-day fundamental physics, the physicists can see the grin of the Cheshire Cat, the electric force, but they cannot see the cat, the motion of which the force is a property. So they ignore the definition of force that they have set up, the definition that is the basis for all of their subsequent applications of the force concept. They assume that the fundamental forces are autonomous entities existing in their own right. Indeed, they go even farther and characterize these forces as the primary physical entities. A typical statement taken from a physics text asserts categorically that, quote, the gravitational force, the electric force, and the nuclear force govern all that happens in the world. This leaves the antecedents of the forces, such as the electric charge, suspended in thin air without any connection to anything else. If the force is the fundamental entity, what is the charge? The physicists cannot answer this question. The general tendency is to evade the issue by contending that there is no answer. As one author puts it, when we have said in what condition objects are when they are electrically charged, we have said all there is to say, end quote. Another tells us this, quote, the question, what is electricity, so often asked, is meaningless. We must have in physics something behind which we do not go. If it were not electricity, it would have to be some other conception. Under the circumstances, it is not surprising that there are major differences of opinion as to the nature of force and its place in the physical picture. In spite of the general agreement as to how it is to be defined, Richard Feynman attempts to rationalize the basic contradiction by advancing the curious contention that force is, quote, more than a definition. Meanwhile, the enthusiastic followers of Einstein claim that he quote, made the concept of force unnecessary by reducing it to geometry. What this amounts to, as L.W.H. Hull points out, is a return to Aristotle's idea that there are various kinds of natural motion in various parts of the universe. It portrays the gravitational force as having a nature and origin totally different from those of other forces, a conclusion which, as Hull indicates, is a step backward in the continuing effort to unify physical theory. Once the existence of distributed scalar motion is recognized, all of these contradictions and discrepancies clear up almost automatically. The electric force is a property of a motion, by definition. The fact that this force is distributed in the form of a field shows that the motion of which it is a property is not an ordinary vectorial motion, the force aspect of which is a vector, but a distributed scalar motion, the force aspect of which is a field. As the electric force is a property of an electric charge, we now find that it necessarily must be a property of a distributed scalar motion. It follows that an electric charge is a distributed scalar motion. So the question, what is an electric charge, is not meaningless after all. It is true, as asserted in the statement quoted above, that we must have something behind which we do not go. But it is a serious mistake to stop too soon. It is a mistake to treat something like an electric charge or the force that it exerts as fundamental when it is not fundamental. When we go a step farther and identify the charge as a motion, the answers to the long unanswered questions quickly emerge. As soon as we know what an electric charge is, the reason why it exerts a force is clear. Because a distributed scalar motion extends over a three-dimensional space, it is an accelerated motion. One of the properties of any accelerated motion obviously is a quantity of acceleration, that is, a force. The reality behind Feynman's question that force is more than the defined quantity also becomes evident. In explaining his statement, Feynman notes that in dealing with force, the tacit assumption is always made that the force is equal to zero unless some physical body is present. We can now see that the presence of this physical body is not something in addition to the definition of force. It is implicit in the definition. Force is a property of a motion, and the existence of identifiable motion involves a physical body. Okay, we'll move on to the next section here, which is called motion and stationary charge. The biggest obstacle in the way of recognizing that the electric charge is a motion is the observed existence of stationary charges. How can a stationary charge be moving? It clearly cannot move vectorially if it is stationary in the reference system, because vectorial motion is motion relative to that reference system. Recognition of the charge as a distributed scalar motion provides the answer. All objects in a scalar system, all galaxies in the galactic system, all spots on an expanding balloon, and so on, are moving relative to each other. But in order to represent such a system in a stationary frame of reference, one of the moving objects must be arbitrarily coupled to the reference system in such a way that it is stationary relative to that system. In the galactic system, the location of our own galaxy is the point that is tied in to the reference system. The position of our galaxy is the reference point. In the balloon system, the reference point is the point at which the balloon rests on the floor. Since the motion of our galaxy, or the spot on the balloon surface that rests on the floor, still exists irrespective of the way in which it is represented in the reference system, that motion has to appear to the reference system as motion of the galaxies or spots with which the reference objects are interacting. Thus, the measured recession of galaxy A includes the motion of our own galaxy away from A, as well as the motion of A away from our galaxy. Similarly, the motion of spot X on the balloon surface outward from some other spot Y does not appear as a movement of X if X is stationary, if X is the stationary point in the reference system. Nevertheless, the motion of X exists and increases the separation between X and Y. It follows that the motion which does not appear in the reference system as a change in the position of X is included in the representation of the motion of Y outward from X. The situation of a charged object is similar. Such an object is moving either inward or toward all other members of its class, or outward away from them. But in the reference system, it appears to be stationary. Its motion therefore manifests itself as motion of the interacting objects. The facts revealed by the scalar motion investigation will be unwelcome to many, perhaps most, scientists. Old ideas, like old shoes, are comfortable, and even though scientists are committed to the advancement of knowledge in their field, they find it distressing to be faced with the necessity of changing some of their basic concepts. But we have no choice. When we undertake to ascertain how nature operates, we have to accept the world as we find it, whether we like what we find or not. Those who are in the forefront of scientific research have long realized that the simple view of physical reality that we associate with the name of Newton is untenable in the light of present knowledge, and that the universe is actually much more complex. The only question at issue is the nature of the complexity. At least some of the simple ideas of long standing will have to be sacrificed. But though it may be hard for most individuals to change their ideas as to the nature of something that they believe they understand as well as they do motion, the readjustment of thought to a minor matter is a minor matter compared to the bewildering mathematical and conceptual complexity that has been introduced into physics in the last 100 years by those who have been trying to solve the outstanding problems without the benefit of an understanding of scalar motion and its properties. Furthermore, there are many compensations for the loss of the old and cherished, but mistaken traditional ideas about motion. Every advance in knowledge clears up some of the previously existing difficulties, and a big advance, such as the discovery of distributed scalar motion, solves a great many problems. One of these is the long-standing mystery of gravitation. What has been said about the electric force in the preceding paragraphs is equally applicable to the gravitational force. Mass, like charge, is a distributed scalar motion that is not recognized as a motion by present-day science. Gravitation is an aspect of that motion. That is, the gravitational force is the force aspect of the motion that is called mass, just as the electrical force is the force aspect of the motion that is called charge. Magnetostatic phenomena, such as the force exerted by a permanent magnet, are in the same category. We will have to recognize that there exists a magnetic charge, a distributed scalar motion analogous to mass and the electric charge. There are, of course, differences between these three types of phenomena, even though all are distributed scalar motions. It will not be possible to explain the reasons for these differences within the limits of the present article, but a full account will be given in a book to be published shortly. In addition to the clarification of basic physical relations that follows directly from the recognition of distributed scalar motion, this forthcoming work will also show that by combining the new knowledge of the properties of scalar motion with some well-known facts whose full significance has not heretofore been appreciated, particularly the fact that the electric charge exists only in discrete units, it is possible to establish on a purely factual basis the true nature of a wide variety of hitherto poorly understood phenomena, but only in the field of basic physics, not only in the field of basic physics, but also in astronomy and cosmology. All right, that is the end of that paper, The Physics of Motion by Dewey B. Larson. And I got lost there a little bit, but the basic idea is that the universe is made out of motion, but it is made out of a specific kind of motion called scalar motion, modeled by a balloon with dots on it. And if you blow up the balloon, all the dots are moving away from each other. Larson really calls that the progression of the natural reference system. And if you suck in the balloon, all the dots are moving toward each other. And that is analogous to gravitation. And that explains force at a distance. There is no force at a distance. It just appears to be that way when you assign a reference point. That's when you get directional motion, is when you assign the reference point, not before that. The scalar motion itself is not directional. And a distributed scalar motion is when you pile on a rotation in addition to that motion. And then so the motion itself gets distributed over a circular path or a surface path. And all of that basically, helps Larson be able to explain gravitation, electricity, electric charge, and magnetic charge as all different forms of distributed scalar motions. We will actually be reading that work that Larson was referring to at the end, called Basic Properties of Matter. And he will go into this in more detail, probably excruciating detail. So, but again, if these things kind of get you lost, don't fret. Just kind of persevere your way through it and just try to grab what you can and mull it over at a later time. Don't dismiss things out of hand just because they're unfamiliar. Just kind of persevere and move through it, and eventually, your subconscious mind will work on it, and you might get more clarity than you originally thought. All right, well, thank you for tuning in today, and stay tuned for another video tomorrow. Thanks for tuning in.